tell us about the economics of distributed systems.
Thank you so much, Ingwu. Thank you all for coming. Thank you for having us give this tutorial. So I wanted to give a second part of this tutorial. I started working on Bitcoin back in 2017, 16, and was kind of fascinated by a lot of things, how it works and its economic properties. And very soon I realized that I need to learn more about the underlying rails. And I taught a class at UChicago a year ago, trying to understand economics of distributed system, trying to get those two literatures. I found it incredibly interesting, and I want to give you a peek into this literature. So the plan for today is first to give some motivation for why we're asking those questions. What are the questions that those classic results from distributed computing can help us answer? Then I'm going to talk about some more recent results, talking about Nakamoto's consensus, like the algorithm that works on Bitcoin, and kind of like connecting it to more recent development in distributed computing. And finally, to bring it back together, I'll talk about what are some questions that are in the intersection of economics and distributed computing, and why I think this is a really interesting subfield for researchers, especially on EC, to look into. And it should have a lot of exciting results in the next few years. So the first motivation that I want to start with is, like, let's suppose that we want to create a payment system. So payment system just records balances and transfers. So every user will have a balance. You want to make transfers to other people. And of course, I want to make sure that all the transfers are legitimate. Like, nobody makes up money, nobody gives money they don't have, nobody steals money from anybody's account. And let's suppose that I have a big stone in the center of my square. So this big stone is the Rosetta Stone, if you happen to identify it. Let's imagine that we have a big stone in the middle of our square. What can we do? We can, every time that we have a transaction, just write it on the stone. And here's what a Bitcoin transaction looks like. It's some representation of it. It has some source, some destination, how much fee you want to pay, and all of that is going to be signed. And the cryptographic signature that Matt talked about in the first half of the consensus basically makes this unforgeable. If you're the owner of the account X, you can write a transaction that says, I transfer money to the other account. If you're not the holder of account X, you cannot write this transaction. It's completely unforgeable. Now, if we take those kind of transactions and write them to the ledger, to this big stone that we have in the center of the square, and the stone is a write-only ledger, everybody can see that, that will be completely enough to create a payment system. Because if I want to make a transaction, I just go and write it. Nobody else can take money out of my account because they cannot sign my accounts. The cryptographic signature really authenticates that I'm the owner. And because all the ledger is public, then everybody can verify that all the account rules are satisfied. Like, I don't transfer more money than I have in the account. So that's essentially how Bitcoin works. That's the Bitcoin ledger. It's all open. All the transactions are reading in sequence. Everybody can authenticate it. The challenge is, how do we get this right on the ledger, or this big stone? So we'll get back to this. Before I talk more about this, let me give you a second motivation, which is a story about Leslie Lamport and NASA. Leslie Lamport won the Turing Award, and this is a bit of an embellished version of a true story about Leslie Lamport. The story goes that he was in NASA, and NASA wanted to send Voyager, this probe on the left, and Voyager was supposed to last an incredible amount of time, which it did. And to make it last as long as possible, NASA wanted to have 3 computers that will control every operation of the probe. So, like, controlling the engine will be done by 3 separate computers. Each one of them was coded independently. And you take a vote to take a majority decision between all of them. So if one of them has a mistake or a bug, it's going to get overruled. 2 out of the 3 will hopefully be correct. As long as one is defunct or faulty, we still have the right outcome. And the story goes that Leslie Lamport looks at the design and says, well, your design doesn't work. Or design says that if one is faulty, then still we have that, like, the vote should be okay. But this doesn't work because you thought of the voting procedure as something that happens kind of like somewhere in the void. The voting procedure can happen only if it's done by one of the parties. There's no agreed upon voting that kind of floats in the air. The voting has to be done in one of the parties or something like that. And if that party that controls the voting is corrupted, of course, the voting result will be corrupted as well. And more than that, lastly, Lamport showed that there's no system with 3 computers that is resilient to a fault by one of them. Like, we'll see this result in a bit. Okay? So those 2 kind of motivations kind of bring together the kind of like consensus problem. And the consensus problem basically says, can we get a collection of independent computers to create something that we'd like that could have been provided by one big computer if we had one good computer? Suppose we don't have one good computer. Suppose we just have a bunch of small computers. Each one of them may be faulty. Each one of them may have communication issues. Can we create some protocol, some interaction between those small computers such that an agent that's interacting with this collection of computers can think that he's interacting with one big computer that is reliable and good? And of course, if nothing bad happens, this is a pretty easy task. The challenge will be, can we make it also to be resilient? So suppose one of the computers that operate this, this collection of nodes, by the way, I'm going to use nodes, computers, agents interdependently, interchangeably. Yeah? Suppose some of the computers become faulty. Maybe they just crash and stop doing anything. Maybe they have some bugs in the code and they start doing unpredictable things. Maybe they're adversarial. Maybe they're controlled by an attacker. We want to kind of think about those different kind of scenarios. And the communication may break down. Maybe this communication between nodes got shut off. Maybe we have some legs in the network. Some routers in the way got broken off. We want this collection of nodes to act as one big resilient computer, as if it was one computer. And one reason that's like traditionally you want this is just traditional resiliency. If you're Amazon and you want to be up 99.9999% of the time, you cannot rely on one data center. You have multiple data centers all over the world, and then you need to make sure that they're all synchronized. The answer that you get does not depend on which data center you talk. Also, economic reasons to do that. So an older paper that ended up getting published in 21, but it's much older than that, said like there's a big economic motivation why you would want to have this collection of nodes. Well, that removes the monopoly power, the pricing power of each one of them. If your service is provided by a collection of actors, each one of them can be easily replaced, and new providers can enter and exit, that makes service provision competitive market. And that means that the service providers have no pricing power, not monopoly power over you. In particular, if you think about the Bitcoin protocol, the fact that anybody can become a miner actually removes pricing power for transaction processing. Visa can decide how much you get charged for using a credit card. Nobody can decide how much you pay for a Bitcoin transaction. That will be determined by some market. Yeah. Yeah. So we have this kind of like goal to create some way for a collection of nodes of computers that can communicate with each other imperfectly to still act as one computer. And this is where consensus comes in. This is like the classic consensus problem. And there's various models of consensus problem, different kind of setups, different descriptions of the environment and what are the nodes and what the attacker can do. And none of them are going to be exactly realistic. They don't intend to exactly capture the world exactly as it is, but they try to be close enough to predict to predict what will work and what matters and what does not. On the other hand, they want to be tractable enough so we can say something about it. And some of them will kind of give you quite surprising results. And one of the really nice things about this literature, regardless of all its importance for all the cryptocurrency world now, is that this is just a really beautiful theoretical literature that's very close to practice. Like people who actually design consensus algorithm, Leshno Lamport in particular, are very prominent in saying that you need to prove the correctness of your results. You have to have some model, because it's very easy to get those things wrong. Proofs are really helpful, and the models is very helpful for the engineering of systems. Okay, so let's start by giving some setup, some formal setup. So this is one version of the consensus problem. There's other formulation. They're all very closely related. I'm just going to focus on this one to just give you one kind of sense of what consensus problems look like. We start from a set of nodes, 1 to n. Notice that this is already an assumption that I have a set of nodes, and I know who are the nodes that are going to try to achieve consensus. So the set of nodes 1 to n, they can all either be faulty or honest. I am going to talk about what it means to be faulty in the next slide. To think that if you're honest, you basically follow what the protocol tells you to do, and you want to achieve consensus, you want to achieve agreement among the honest nodes. What does it mean to achieve agreement? Let's start each node with some value, 0, 1. It doesn't really matter that it's binary. You can, of course, generalize non-binary values. And the protocols will follow some protocol. They'll interact with each other. They communicate in whatever communication mode they're allowed to. And eventually, you want that they will decide on some value. The value will be either 0, 1. What we would like is properties that will ensure that this collection of nodes will act as one. And generally, you divide those properties into 2 main categories, plus a third one. Validity is going to be a third. The first, consistency, or more generally, safety, says nothing bad happens. So consistency will ask that if 2 nodes decide, they must decide on the same value. Think of deciding as a node saying, oh, I think that the purchase on Amazon went through. I can send an answer to the customer that the purchase went through. If one node does this, it should better be the case that everybody else agree. We don't want the customer to get contradicting messages. Liveness says that an honest node must decide. If you're a node and you're not faulty, then you should give an answer. Of course, it's very easy to be consistent by not doing anything. It's very easy to be live if you don't have to be consistent. What's interesting is the combination of the two. And it's very useful, though, to write those 2 things apart, because then we can say what are the faults that we might have. So I see a question in the chat. By the way, if you have questions, please do write them in the chat. There's a lot of relation between consensus and common knowledge, but it's not exactly the same thing. I'll be happy to say more about this offline. There's a lot of connections there, but it's not exactly the same thing as common knowledge. The last requirement is something that we need to make this problem non-trivial. If we just ask for consistency and liveness, we could just say all the nodes just decide on 0 all the time. You need to add another requirement to make this problem non-trivial, and validity is a pretty weak requirement. We just ask that if all nodes start with the same value, any of those nodes must decide on that value. So if everybody starts with 0, you must decide 0. If everybody starts with 1, you start with 1. If you start with a mixture of 0, 1s, just agree. Anything goes. Okay, so what are the challenges that we need to deal with? What is the environment that we act in? So there's different kinds of challenges we can put in. So One is what kind of communication the nodes can pass along to each other. If we would assume that there's like a message in the sky that everybody sees, the problem will become trivial. In a sense, the consensus problem is about creating this message that everybody will see. So what we will assume that there's bilateral messages, and there's different kinds of assumptions on the messaging technology that will be very important for the results. So if you know the two generals problem or the email game of Rubinstein, that's when messages can get lost. There's two really important models, synchrony and asynchrony. Both of them assume that messages are always delivered, but in synchrony, there's a bound on the delay. In synchrony, if I wait for one round, I know that the message was delivered. So there will be common knowledge by the sender of the receiver that the message was delivered at the end of the round. Under asynchrony, all messages will be delivered, but there could be unbounded delays. So messages can come out of order. You can't really know what state other people are in. Maybe they heard my message already. Maybe they didn't. Maybe they read them out of order. In particular, you can't know whether somebody is just like not replying or whether they're just being delayed. And another challenge is that we may have faults. Some of the players may be faulty themselves. So some of the nodes may just stop working. That's called crash faults. And some of the nodes may act adversarially or like do kind of like malicious thing or anything possible. Like that's called Byzantine faults. Like if you heard of Byzantine fault tolerance, that's where the Byzantine comes from. Byzantine is kind of like used as a synonym for evil. The story behind it is like that the original paper tried to choose a nation to be evil that does not exist anymore, so nobody will be offended. I'm a bit offended for the Byzantine Empire. I don't think they should be scapegoated here, but anyway. Byzantine faults basically says like the nodes can be malicious as they wish, but of course, like the normal computers, they cannot break encryption, they cannot force signature, they cannot pretend to be other people. If I have a message channel, usually I can authenticate who the message came from. And on authentication, there's also a stronger version of authentication, PKI, which basically means that we have a cryptography framework that allows us to sign messages. And the difference between that and just having reliable links is the difference between whether I know that that somebody sent me the message or whether I can forward the message to somebody else and prove that that I got this message. So if Shengwu sent me the message under the reliable links model, I cannot tell anybody else reliably what Shengwu told me. I may be able to lie about this. But if I have PKI, then Shengwu would have signed this message, and I can forward it to anybody else and show them that here's the signed message for Shengwu. I could not have forged this. What can a consensus protocol do? Well, think of this as a game with partial information. Each node will know its current state. It will know which messages it received. That kind of gives it some possible state and some information about what the other nodes may have seen or may have not seen given the protocol. But I have only partial information on the nodes. I don't know what the other nodes I actually saw. Each node has a strategy that says, given your state, given what you see, you decide what to do. If you got those messages, you may send more messages, you may wait, you may do some computation, or you may say, okay, if I got those messages, that's it, I can decide and finish the protocol. And of course, once you decided, you can interact with other nodes to help them decide, but you cannot change your mind again. Okay? So think of this as a game with incomplete information. That's where the challenge comes from. And now let me go through some classical results on this to show you how all those assumptions in different modeling environments really change the kind of results, whether you can achieve consensus or not. So first is the two generals impossibility result. So no protocol can achieve consensus in the two generals problem when messages get lost. I'm not going to go through any of the proofs today. The proofs are really nice. Like a lot of the proofs here are really beautiful. I have a bunch of slides on my Canvas page for the class if you want to see more material. Or you can see Lane Shee's book, and there's a bunch more resources out there. The proofs are really nice. Let me just give you like some kind of like short intuition for like why this result holds. And the one way to prove this is just first you observe that it's impossible to get the two generals to achieve consensus without sending any messages. If you don't communicate at all, it's clear that you don't know what state the other guy is in, and therefore like there's no hope to coordinate. Well, what happens if you do send messages, but they can get lost? Well, let's look at the last message. If the last message gets lost, and let's say the general on the left is the one that sent the last message. Now, this general does not know whether the message was received or not. He must now make his decision, must decide on the value, regardless of whether the value got sent or not. If the protocol works, it means that he will decide the right value and will be consistent with the other general, regardless of whether the message is sent or not. That means that the message was redundant. We didn't need this message. If we didn't need this message, let's have an easier protocol which removes this message and just continue by induction, deleting all the messages until we get to a protocol that doesn't send any messages, which is, of course, a contradiction. So that's kind of like a hand-wavy version of how you get the impossibility result, prove the impossibility result for the two generals problem. And it's a bit of kind of like the ideas behind a lot of those protocols. You look at the kind of like borderline cases. A lot of the problem, those problems will arise because there must be some borderline case. A couple of other really important impossibility results. So if you think of asynchronous consensus, so like I have nodes that try to communicate among each other. All messages are guaranteed to be delivered. We just saw that if messages get lost, then there's no hope. But suppose all messages are guaranteed to be delivered, we just don't have a bound on how long is the delay. Then this seminal result by Fisher, Lynch, and Patterson, commonly known as FLP impossibility, says that no deterministic protocol can achieve consensus even if the only problem that can arise is one crash fault. Even if only one node can crash, that's enough to break down the protocol. Essentially, that basically says, like in the asynchronous communication protocol, you cannot achieve consensus. Like the minimal fault that you can ask for is already too much. So what can we do? Well, of course, you want to kind of require more of the communication model. It means that this communication model is kind of allowing for too big of a fault, for example, too big of a problem with the communication. If you look at the synchronous communication protocol, or synchronous model, then there's still impossibility results, but they're not even remotely as bad. So under synchronous communication, there's limit. It says if you have a synchronous communication protocol, then you can tolerate up to a third. You must need strictly less than a third Byzantine faults. If you have 1 in 3 faulty, there's no communication protocol that can achieve consensus. And this basically is the impossibility result for the NASA example. Like 1 in 3 is impossible. Okay. Beautiful proofs for both of those terms, but given the really short time, I'm just gonna like refer you to look at them. There's also complementary possibility results, starting from the counterpart to the synchronous communication in FLM. If you have strictly less than third, so if you had 4 computers and you wanted to be resilient to a fault of one of them, then there is a protocol that can achieve consensus for synchronous communication and up to strictly less than a third Byzantine faults. So the faulty nodes do whatever they want, but like the honest nodes will still reach consensus. If you allow authentication, so signed messages, you can get a much stronger result. Now you can have agreement. Broadcast is another version of consensus for any number of faults. It doesn't matter how many faults there are. So it turns out that the fact that messages can be signed and people cannot lie about what they heard is really, really important. Now, I should say that the way that you take all those, like that I hear from the engineers or people that work on those protocols, is that if they can take all those results as sanity checks, or just like kind of explain to you what's important, what can be done and what not. The left strong is a protocol that takes a long time. It actually requires synchrony, it requires rounds, and it requires T+1 rounds if you want to be resilient to T faults. So it can take a long time for this protocol to run, but it shows you what's possible. FLP impossibility is, of course, something that you can circumvent in practice. It just says that no protocol can guarantee consensus under any condition, under adversarial faults and under adversarial communication. Well, maybe you can circumvent it in practice in many ways, and there are like probabilistic algorithms that circumvent this and so on, but it kind of helps you kind of understand whether you made assumptions that are too strong, or maybe you need something more for your protocols to work. It shows you what's necessary to achieve consensus. One kind of very practical protocol that kind of combines the insights from both of those is what's called partial synchrony. It says like that I'm not going to require synchrony all the time because maybe I have some network lags, maybe some router went down. I want to allow for that and want to consider that and think that sometimes router will go down and my system should not explode. And this kind of partial synchrony is a very nice model. It makes, or eventual synchrony is often, it's often called also, makes the trade-off that says, like, I may have synchrony most of the time. Sometimes it's going to fail, but eventually I'm going to get it back. And then you get practical algorithms, like Pax's protocol is a protocol that achieves consensus under this partial synchrony. Basically, what it says is I'm going to work well when things are synchrony and messages delivered within a reasonable time frame. When I have some partition in the network, of course, things are going to be impossible at that point. If I can't really communicate between two parts of the network, then I can't achieve consensus. But if this is temporary, nothing bad should happen while the partition is happening, and I should recover gracefully. Once like the communication gets resolved, the protocol should recover well, and that's what Paxos does in a nice way. Okay. What does this mean for Bitcoin? So all those previous results started from the assumption that I actually have n nodes that are trying to agree. The starting point of Bitcoin was that we want to have consensus without knowing the number of participants, without knowing the nodes in advance. As I told you in the beginning, it's actually a very important property if you want to think about the economic properties of this. Because you have free entry and anybody can become a miner in Bitcoin, miners don't have any power to set prices. That's like what we showed in a previous paper. So that's a very desirable property from an economic perspective. So we need to change the model if we want to get some consensus properties in this kind of setup. What would even like a third faulty mean if we don't know a third of what? We don't know the set of blurs. And the way that Nakamoto consensus changed the protocol is that it changed what it assumes about the nodes or the adversary. It said each node will not be a node by designation or by name. It will be some amount of computational power. And the proof of the impossibility results, if you kind of go through the impossibility result, they require the adversary to simulate maybe a bunch of nodes, to act as a bunch of nodes. If I prevent the node from being able to simulate other nodes, because it has limited computation power, I can circumvent those impossibility results. And that's what Bitcoin does. So let me give a very high-level explanation of like the Bitcoin consensus protocol and a couple of results, and then we'll take it back to an economic framework. So remember, we start from the beginning. We want to create a big stone and write on the ledger. A block is just going to be a batch transaction with a pointer to a previous block that creates just a chain of blocks. How will Bitcoin get consensus on what is the next block? Well, they're going to randomly select some miner, some node, to add a block. How do we do this random selection? By hashing. So in Matt's tutorial, we talked about how hash functions can be random number generators. If you get a low enough number in a hash, you basically got selected to extend the blockchain. And how many hashes you can draw per unit time is basically your compute power. When we talk about the majority, we can talk about the majority of the computer power, the majority of the hashes that are being drawn. Now, if you can see here, I have like this chain of blocks, and now I have two blocks that are parallel to each other. Because the random selection is imperfect, different miners may draw blocks at the same time, meaning that they didn't hear of each other. Even if I'm honest and I'm always trying to do the right thing, it may be that I just happen to draw a hash that allows me to add a block at the same time that somebody else in the network did, and we just didn't have time to hear about each other before finding parallel blocks. So in that case, I'll have two blocks that are both trying to extend the chain. How do we agree, reach consensus about which one of them is going to be the chain that we all going to focus on? Well, Bitcoin protocol says go with the longest chain. When you have those two blocks, you're still unresolved, you're not sure. Once somebody else will try to mine a block, they will try to exchange the longest chain they know, or choose between the two kind of possible blocks if there's two possible. Once we added another block, now we resolve this contention, and we can hope to have now one of those chains growing longer, the other getting deprecated, and we reach agreement when the blocks get deep enough. Okay? So the Nakamoto consensus, like the Nakamoto consensus protocol that runs Bitcoin, follows this what's called the longest chain rule, and the original paper by Nakamoto had some arguments why this achieves consensus. It took a few years for the distributed systems and cryptography community to kind of like come up with a bit of more formal definitions that actually found that like you actually need a bit more than what Nakamoto argued in his paper. And the formal definition is that if a block is deep enough, it should be regarded as finalized, as decided on. We're going to have some version of consistency where the consistency is going to be that we have some tail end of blocks that are unclear. That's like not still decided on. But once a block is far enough deep, then we're going to think of this block as being decided. What is liveness going to mean in this context? It means that blocks keep getting added to the chain, and if there's a transaction, then the transaction is included in some block that's get added to the chain. One bad circumstance of this will be maybe we just add empty blocks. The chain goes long, but we don't have any more data in this chain. So those initial definitions are from a paper by Garay, Kiasis, and Leonardus in 2015. And they show that if you have a sufficient majority of honest miners, this is slightly more than a half. Then you do get like, those two properties that will give you a version of consensus in Bitcoin. So it's not exactly the properties that we talked about before. You need to relax some things and go to a probabilistic consensus. But what it basically says is that if you have an honest majority or sufficient honest majority, then the check marks on those deep enough blocks are likely to hold with a probability that is very high and gets exponentially close to 1 or exponentially small as k gets deeper. And the second property is that even if you have an adversary, as long as the adversary controls less than half of the computational power, then the adversary cannot block transactions from getting into the blocks. The blocks will still have useful information in them. Okay? So the original Garaike, Assis, Leonardo's paper talks about the synchronous model. There's a follow-up paper by Pass, Seaman, and Shalat that extend the model to also talk about the delay, the lag in the network. So when I, as a miner, send a block, how long does it take it for other miners in the network to see the block? And the amount of majority power that you need to protect the network depends on how long is the block type relative to delay. So if a block is mined every 10 minutes, and that's 60 times the delay, the lag between when I find a block and when it reaches everybody else in the network, then it's basically almost resilient to 50% attack. You need slightly less than 50% to attack the network. If the lag was much smaller, the adversary will become stronger because the adversary is not subject to those lags, and it will exploit, or potentially can exploit, the fact that the honest miners talk with each other with a lag, while the miners may be more coordinated. So the blue line here is what the when consensus is guaranteed, and the red line is when the paper can show that there's attack that can attack Bitcoin if those parameters are kind of given. Okay. So all of that is great, but let me kind of get back a bit to economics and kind of like wrap it up by asking how this actually interacts without thinking about those systems as economic environments and economic properties. So one thing that you may want to think about or worry about is the security of all those online distributed systems as, for example, payment providers. So for example, think that I'm a merchant and I'm trying to receive a payment from some customer. What I care as a merchant is not whether I think the credit card is valid or not, but whether the bank will actually credit me with a balance. So when I'm presented with a credit card or a check, I need to verify whether the rest of the network will actually acknowledge this transaction as valid or not. Well, having my terminal, my node, having to decide whether this finalizes or not, and make sure that my decision is the same as the decision of everybody else in the network, is exactly consistency. So if you want to have a system that's secure in the sense that I can validate whether a transaction is finite and be confident that everybody else would agree with me, that's exactly the consistency property that we talked about in the distributed system, the consensus setting. Okay? So if I want to think about security of payment systems, for example, I exactly need to think about the distributed systems properties of, for example, consistency. But one problem with all the definition I gave you before is that the impossibility and possibility result all showed that we really depend on whether we have an honest majority. But whether we have a majority of honest nodes or majority of an attacker nodes is completely endogenous in decentralized setting. If you think of honest majority for Amazon data centers, well, as long as up to a third of our computers crash, that's a very rare occurrence, we can be fine because we know our computers, we know the probability that each one of them will have a bug or a problem. Yeah? So a third is meaningful here. What does a third mean for Bitcoin or such open systems? Well, it means basically how much the attacker needs to pay maybe to procure this computation power. Because if the system is open, if you think of decentralization, that's not kind of formally defined most of the time. But when I think of decentralization, I think of something that goes towards a system with free entry, a system that anybody can operate. In particular, the attacker can operate it too. It's not a gated system. So it means attacker may control resources and get influence over the system. So what kind of guarantees can we give? Well, if we want to give a definition of meaningful security in an open system, we want to think about consistency, but we want to also think about the fact that all the majority conditions are endogenous. So the condition that we came up with work with two computer scientists, Elaine Shih and Rafael Paz, was that we defined the economic security of a protocol to be the minimum attacker's cost needed to violate consistency. We can't say whether there's honest majority or not, but maybe the protocol can make it costly for the attacker to pay and get a majority. And now, a natural question is, what does it mean for protocols? We know, we look at Bitcoin protocol and find that it actually has a pretty low economic security. This is very much in line with other works you may have seen. Rafael Eric Budish has a paper going back to 2018. And essentially, Bitcoin has like two problems. One is that the longest chain rule can be very much exploited by the attacker. And if the attacker attacks the protocol, he essentially becomes the honest miner. Like the protocol regards the attacker as the honest miner. And that's, of course, problematic because honest miners are not supposed to lose money. If you can pretend to be honest, maybe you can attack without losing money at all. And second, in Bitcoin, all the miners are anonymous. You don't know the identity of each one of them. If you think of a setting where you have a lot of small entities that are all anonymous, you're going to have tragedy of the commons. Incentives are going to be very ineffective. So we find that the economic security of Bitcoin is pretty low. Why wasn't Bitcoin attacked? There's a bunch of other explanations that are not completely satisfying from a decentralized point of view. And what we ended up coming up with is kind of thinking like, well, one way that you can get economic security is just make sure that you have consistency, even if the attacker buys more compute power. So if you can come up with a protocol, which there are many protocols actually that are always consistent. Even if you don't have honest majority, something will have to break, but you don't have to necessarily break consistency. You can break liveness instead. So if you make this trade-off, you can actually create protocols that have really good economic security properties and actually do not rely on incentives for their economic security. So in a nutshell, what we come up with is that mining rewards are neither necessarily sufficient for security. And I think there's a host of really interesting questions that kind of follow up from this. So let me kind of just wrap up by saying a couple of words about why I think there's like a lot of exciting new stuff to do here. So first kind of thing is that I told you a bunch of results from distributed computing about can we implement like just one computer. There's a lot of really interesting questions that come up when you try to combine this with economics mechanism design. So one thing is that the nodes may not necessarily just be malicious or kind of faulty. They may just be profit maximizing, lazy, or just bounded by incentives or driven by incentives. Doing all those protocols and consensus problem with incentives is incredibly interesting and incredibly I think an incredibly fruitful line of research. And the second thing is that the things that you may want to implement with those kind of systems can be really interesting and potentially useful. So there's a lot of ways where you can just take a system that we know how to create already and just make it distributed. And then people will ask, why does it matter? Why do you care about whether it's distributed or not? But there's a lot of really interesting prospect to creating new properties. So I started going into this entire literature from realizing that in Bitcoin, nobody gets to set prices. You create a marketplace which nobody controls. And if you think about those those protocols, those consensus problems, they basically say, what can a collection of independent agents achieve together? It's kind of like the seminal questions of economics of what can markets do? What can a collection of self-motivated parties achieve by coordinating together? And there's a lot of really great things that we can do using markets. There's a lot of amazing things that open source projects have achieved. And I think this is a lot like open source projects. You have some people that are just writing some code, like Bitcoin's code, and suddenly there's a system that's running out. So we have Linux and Python and TCP/IP and even the English language as basic infrastructure for our life that nobody controls, that are incredibly valuable in our life. And that were not designed by any kind of firm, that were contrived by an autonomous collective. And now think about what we can achieve if we take those open source projects, those kind of collection of people trying to work together, and add so many more capabilities to them. Now we can have a platform that interacts. We can add means to compensate contributors. We can create markets. So I really think of this as a market design frontier. I think this is an incredibly interesting venue for research, and there's a lot of really deep and interesting questions here. And I hope that I managed to give you at least a sliver of kind of introduction to all of this. And let me just put a few of the citations for the papers that I mentioned in this talk. And if anybody's interested, I have like some materials for the class I taught. I'll be happy to share them. If anybody wants, just email me. And if anybody's interested, I'm very happy to talk. Okay? So thank you all for listening.